Hi, we will continue our discussion on evolutionary game theory associated with microbial populations, and in the last lecture we had finished our case 1, which was represented in terms of our payoff matrix as the one where A is greater than C and B is greater than D. And we saw a couple of reasons why this particular set of relationships suggests that this corresponds to all A type of outcome associated with population growth. Let us take a look at another one, which is case 2, and this is defined by A as less than C and B as less than D. And since the relationships that we are defining in case 1 are exactly the opposite associated with the one the relationships that we are defining in case 2 are exactly the opposite associated with those in case 1, you would expect that this corresponds to the case all B. Okay. One of the ways to think about this, it's useful to think about this in terms of our payoff matrix, where we are saying that when genotype A and B grow in the presence of genotype A and B, the associated growth rates are A, B, C and D. And what we are saying when we say that C is more than A, what we are implying there is that in an environment where there are all A's, in this particular environment B grows better compared to A. So, this is an environment where everybody else is an A genotype, and to this particular environment if you add an individual of genotype B, that individual grows at growth rate C, and if to the same environment you add an individual of genotype A, that individual grows at growth rate A, and if C is more than A, is essentially you are applying that in this particular environment B grows better compared to A. And the other condition is that D is bigger than B, which implies that in an environment where there are all B's, in this environment if you were to add an individual of genotype B, that would grow at growth rate D, and in this environment if you were to add an individual of genotype A, that individual will grow at growth rate B, and since D is bigger than B, you are saying in this particular environment B grows better compared to A. And again what these two conditions imply is that irrespective of the environment that we are talking of, genotype B is doing better as compared to genotype A, and hence we converge to a situation where in this particular environment B dominates A and the system moves towards all B. So we have recreated sort of the 2 of the 4 scenarios that we started with in our analysis, all B and all A. Let us see if we can get an estimate, if we can sort of somehow imagine conditions on our payoff matrix such that we can recreate conditions which would lead us to scenario 3, which was coexistence, and scenario 4, which was bistability. So, our next case is this case 3, which is defined by the conditions on the payoff matrix as C is more than A and B is more than D. Now, what this tells us is that if we look at this in terms of our dynamical equation, dxa by dt equals xa times 1 minus xa times xa into A minus B minus C plus D plus B minus D. That is the dynamical equation that I have, and I can write this as x a times 1 minus x a times x a into a minus c plus 1 minus x a into b minus d. That's essentially what we are talking about here. So, what does this tell me about dynamics of the system? What this tells me is that when the population is mostly A, I am using the word mostly in quotes here, which implies that x A is approaching 1, is not quite 1, but is approaching 1. Most individuals in the population belong to genotype A, and there are only a very few individuals which actually belong to genotype B in this scenario. That is the scenario we are calling mostly A here. So, if we have mostly A, that means x A is slightly less than 1 because x A cannot exceed 1. In that scenario, let us look at this, what this dynamical expression is telling me. In that case, this is greater than 0, this is greater than 0. So, these two are no problem. In that scenario, 1 minus x A approaches 0 because x A is approaching 1, hence 1 minus x A is approaching 0. So, I can ignore this particular expression as almost 0. And then I am left with x A into A minus c. But under the conditions that I have been given, c is bigger than A, hence this is less than 0. What that implies is that as x A approaches 1, dx A by dt is less than 0. That is what this relationship is telling us here. On the other hand, if you are dealing with the scenario, if the system is present in a state where it is mostly B, what that implies is that x A approaches 0 and x B in turn approaches 1. In that case, what happens to this expression? In that case, x A would still be greater than 0, 1 minus x A would still be greater than 0, but of the two contributions that are coming here from this term, x A, which is approaching 0, this quantity now can be ignored because that is almost approaching 0. Whereas 1 minus x A is multiplying with b minus d, and b minus d in the given set of conditions is greater than 0. Hence, this expression in the bracket in this condition is greater than 0, which implies dx A by dt is greater than 0 for this condition, whereas for this condition dx A by dt is less than 0. What does that mean? What that means is, let us try to sketch this graphically. What the result that we have derived says that when the system is in a state where it is mostly A's and very few B's, dx A by dt is less than 0, which means if it is mostly A's, dx A by dt is less than 0, hence as t increases x A decreases. That means the system wants to move away from a situation where there is only all A's and no B. On the other hand, when the system is present in a state when there are very few A individuals and it is mostly B, dx A by dt is greater than 0. That means the system wants to move to a state where the frequency of A individuals is actually increased with time. Okay. So, that is what this analysis is telling us analytically. Graphically, what that means is that if this is x A, this is essentially f A minus f B that we analyzed, this is 0. What this is telling us is that the sign of f A minus f B, which is the same as the sign of dx A minus dt, you should convince yourself of that, is that when x A is small, this quantity is positive, and when x A is large, this quantity is negative. That means starting from small values of x A, the system wants to move towards higher values of x A, and starting from larger values of x A, the system wants to move towards smaller values of x A. Now, ideally these two values should converge somewhere at a value called x naught, and that takes us back to the third steady state that we had derived for this type of analysis, and let us see what that steady state is telling us for this condition here. And the value associated with that steady state x naught was d minus b divided by a minus b minus c plus d. That was the expression we derived in the last lecture, and let us see if this value does end up lying between 0 and 1 for the conditions that we are discussing. So, what does the numerator tell us? Remember, the conditions we are working under are c is greater than a and b is greater than d. Those are the conditions that we are working under. Now, if that is the case, b is greater than d, that means the numerator is negative, because d is less than b. But what about the denominator? I can write the denominator in the following fashion. I can write this as a minus c a minus c minus b minus d. If I write it like this, then what this is telling me is that the whole expression is a negative number divided by a minus c is again a negative number. So, this is again a negative number minus b minus d. B minus d is a positive number, which is this b minus d is a positive number, but there is a negative sign here. So, this is plus another negative number. I can rewrite this as negative of a positive or positive of a negative. So, what this tells me is that x naught is actually a negative number divided by two negative numbers, and the magnitude of the denominator is more than the magnitude of the numerator, because in the numerator here is d minus b, and in the numerator this term is essentially also d minus b, and to this d minus b we are also adding another negative number, hence the magnitude of denominator is more than that of the numerator. What this implies is that x naught under these conditions will always belong to the range 0 and 1, which means that this particular steady state does exist, and our stability analysis here shows that particular steady state not only does it exist, but it is also stable in nature. So, this x naught is the stable steady state associated with the system, and these two are the unstable steady states associated with the system. Okay. So, that covers the third case associated with our analysis in terms of payoff matrix, where we have shown conditions that constrain the behavior of payoff matrix, which would lead us to coexistence of the two genotypes associated with the environment. Let us look at the final case and see if we can also find conditions which would lead us to bistability associated with the system. So, this is case 4, and this says that A is greater than C and D is greater than B. And I am not going to do the complete analysis of the system, but we are just going to make some intuitive arguments about what is happening in this system. And if we look at, we are going to make those intuitive arguments by looking at the payoff matrix. The payoff matrix here suggests that, so these are competing strategies, and then the payoff is just A, B, C, D. What this is telling me is I am going to look at this in terms of columns. So, when an individual is playing, or in this case a particular individual is growing in an environment where there are only A's, in that particular case A is bigger than C. So, if only A environment, A does better than B. That's what this payoff matrix is telling us, that if you're growing in an environment which is mostly A and you happen to be a B individual, then you are going to grow with a growth rate A. But if you happen to be an individual of genotype A, you are going to grow with a growth rate A. And since A is greater than C, in this particular environment, an A does better than B. But on the other hand, if you are growing in an environment where there is all B's, then the converse holds true, that if you are growing in only B, then B does better than A, and that is because D is now more than B. So, what does that tell us? What that tells us is that if I am growing in an A environment and there are a handful of B type individuals, those B type individuals are likely to get eliminated from the environment, because in that particular environment where most of the individuals belong to genotype A does better than B type, and hence those few B type individuals are going to get eliminated, and we are going to move to a situation where there is all A and no B. On the other hand, if I am growing in an environment where most individuals are of genotype B and there are a handful of A type individuals, in such a scenario the B type individuals are actually growing better than the A type individuals, and hence selection is going to eliminate the A type individuals and you are going to end up with all B's and no A. That is what this payoff matrix is telling us, and that leads us to the case of bistability, that now whether you end up in a state where there are all A's or all B's is actually dependent on what was the starting composition of the population that you began your experiment with. Within one confines of the population, you are going to end up eliminating B, and if you are starting too close to all B's and only a handful of A's, then you are going to end up eliminating the genotype A from the population and you will end up with only B's. So, that sort of also tells us about what are the conditions on the payoff matrix which would imply that there exists a scenario where you can have this bistable sort of a behavior. What I leave as an exercise for you is analysis of the dynamics of this system, and what I would like you to show is that in this particular scenario, case 4 that we just discussed, if we have x A going from 0 to 1 and those two particular conditions hold, and this is the sign of dxa by dt, what I would like you to show is that there exists an x naught, the third steady state for this system does exist, and that this is unstable in nature. Moreover, if there is any deviation to the left of this system, you move towards x A equal to 0, which means all B, and if there is any disturbance from this steady state towards the right, you move towards this scenario, which is all A and elimination of B. So, in that sense, these two steady states are my stable steady states under these conditions. This is A greater than C and D greater than B. Okay. I leave this particular analysis as an exercise for you. Okay. All right. Now, since we have talked structure of payoff matrix and the associated dynamics that result from it, what we want to discuss is the appropriate condition for stability in terms of my payoff matrices. We have talked the equivalent definition of stability associated with steady states in dynamical systems, and we have been doing that throughout the course. We want to discuss stability in terms of these payoff matrices that we are defining. And the most widely applied definition that is used in this context is what is called a Nash equilibrium. And let me define that here. So, a Nash equilibrium is defined as the following. Imagine there is a game between two people, game between two people. In our context, we are going to replace this people with the two genotypes, and it goes on that if both play the same strategy, in our context the strategy is replaced by the particular genotype. So, if two bacteria are both of the same genotype, this strategy, the definition goes on, is said to be Nash equilibrium if neither of the two players increases his or her payoff by switching to the other strategy. Okay, what does this mean? What this means is that if in the context of game theory, if there are two individuals which are both playing with strategy A with each other and the other available strategy is called strategy B. Now, if I am playing my opponent with strategy A and if there is an incentive for me in switching from strategy A to strategy B, my opponent sticks with strategy A, but if on switching with strategy B, I increase my payoff. If there is an increase in my payoff, that means that A is not a Nash equilibrium, because there is no incentive for the two agents or two players which are competing here to remain with strategy A. Switching to strategy B increases payoff, and hence the agents are not going to stick with strategy A, and hence this is not an equilibrium strategy. On the other hand, if both of us are playing with strategy A and on switching to strategy B, my payoff actually decreases, then A is said to be a Nash equilibrium, because on switching strategies now my payoff decreases, and hence I will never do that. In terms of the bacterial example that we have been talking about, imagine that we are all A genotypes existing in this environment and all of us are growing at a small growth rate A. Now, if there is a genotype B individual that arises because of a mutation, this B individual is present in a pool of A individuals, and this particular B individual is going to grow at a growth rate C. Now, if C is less than A, and A, remember, is the growth rate of an A individual which is surrounded by A individuals. If C, the growth rate of this mutant that has arisen, is less than the growth rate of the individuals belonging to the parent genotype, then this particular new individual is not going to be able to penetrate into the parent population and increase its frequency. And in that context, genotype A here is going to be said to be as a Nash equilibrium associated with that problem. So that's the definition of Nash equilibrium. Let's just do a quick example matrix to sort of make this concrete, and let's imagine that if my payoff matrix P is given as the following. Three, 5, 0, 1. Now, what we want to comment on is whether is A Nash equilibrium, and the other question is B a Nash equilibrium. Okay. So, you should pause the video for 30 seconds or so and think about these two questions according to the definition that we have just laid out, and try to answer these yourselves. Now, if A was a Nash equilibrium, what that means is that both the agents, both the players are playing with strategy A. So, A is playing A and the payoff associated is equal to 3. Now, if this is me and this is my opponent, then if I switch my strategy to B, my opponent sticks to strategy A. If that happens, then my strategy is B, opponent's strategy is A, and hence I increase my payoff from 3 to 5. Nash equilibrium says that if you can increase your payoff by switching, then that particular strategy is not a Nash equilibrium, hence A is not a Nash equilibrium. On the other hand, if both the agents are playing with strategy B, this is their payoff 1. Both of them are getting payoff 1. And now if I decide to switch from strategy B to strategy A, then my opponent of course is still playing with strategy B. Then in that case, my payoff when I am playing A and the opponent is playing B, my payoff is actually equal to 0. Hence there is no incentive for me in switching from strategy B to strategy A, hence B is a Nash equilibrium. Okay. So looking at your payoff matrices, in terms of the biological example that we have been talking about, you can comment on whether a particular strategy is going to be an equilibrium strategy in terms of should a mutant of the other genotype arise in the population, would that mutant be able to grow faster than the parent individuals or grow slower? If the mutant is able to grow faster than the individuals of the genotype that already exist in the environment, then that strategy is not going to be Nash equilibrium, because then the mutant frequency is going to increase and eventually it might get eliminated from the environment. Another way to define stability is something called an evolutionarily stable strategy. Evolutionary stable strategy is referred to as an ESS. And what this says is that imagine all individuals are playing strategy A or are of genotype A in our context, and one mutant is introduced, or you have one agent which is playing with strategy B. Then the question that arises is that is B at that point able to invade population of this A type individuals? That is the question. And if B is able to invade into the population of these A type individuals, then A is said to be a strategy which is not an ESS. On the other hand, if B is not able to invade into the population of A type individuals, in that case this A strategy is an ESS. So if my payoff matrix looks like this, how can we comment if a particular strategy is an ESS? So all individuals are of type capital A, and now we have one B type individual. So when this B type individual is introduced, what is fitness of A type individual? What is FA? FA is just going to be equal to A times XA plus B times XB. But since XB is only, XB corresponds to the frequency which is obtained when you have only one individual of type B and everybody else of type A, I am going to say that XB is a very small number epsilon and XA consequently is a number 1 minus epsilon. This is because epsilon is the frequency which is associated with one individual of genotype P and everybody else of genotype A. So this is FA, which is A times 1 minus epsilon plus B epsilon. Consequently, the fitness of B at that point is just going to be C into 1 minus epsilon plus D into epsilon. And the condition for A to be ESS, the condition is that FA at this instant should be greater than FB, which is A times 1 minus epsilon plus B epsilon should be greater than C into 1 minus epsilon plus D epsilon. Okay. So, let us finish this in the next couple of steps. So, the condition for A to be ESS as we have derived is A into 1 minus epsilon plus B epsilon should be greater than C into 1 minus epsilon plus D epsilon. Since epsilon is a very small number next to 0, what I am going to do is drop these two terms. Their relative contribution to these terms is negligible, and hence I drop them, because typically in a bacterial environment I am saying that n is of the order of 10 to the power 6, 7, 8, 9, and one mutant individual's contribution towards this epsilon is going to be very, very small. If that is the case, then the condition for A to be ESS is just A bigger than C. That is the condition such that A is an ESS. On the other hand, if A is equal to C, then these two terms drop out because these exactly cancel each other out, and then the condition for A to be ESS becomes B bigger than D. Okay. So, these are the two conditions for A to be ESS. So, in this lecture we have talked about two conditions that we have for a strategy to be defined stable in one sense. One was the Nash equilibrium. We can define a strategy to be whether it is a Nash equilibrium or not, whether an agent has any incentive in switching from that particular strategy to another, and the second one is this evolutionary stable strategy via the definition that we just completed. We will continue this discussion in the next lecture onwards. Thank you.